correct agreement. We then highlight some previous results relating to consensus algorithms and finally state the goals of consensus for the Ripple protocol within our formalization framework. 2.1 Ripple Protocol Components. We begin our description of the Ripple network by defining the following terms. Server. A server is any entity running the Ripple server software as opposed to the Ripple client software, which only lets a user send and receive funds, which participates in the consensus process. Ledger is a record of the amount of currency in each user's account and represents the ground truth of the network. The ledger is repeatedly updated with transactions that successfully pass through the consensus process. The last closed ledger is the most recent ledger that has been ratified by the consensus process and thus represents the current state of the network. Open ledger is the current operating status of a node. Each node maintains its own ledger. Transactions initiated by end users of a given server are applied to the open ledger of that server, but transactions are not considered final until they have passed through the consensus process, at which point the open ledger becomes the last closed ledger. Unique node list. UNL, each server S maintains a unique node list, which is a set of servers that S queries when determining consensus. Only the votes of the other members of the unique node list of servers are considered when determining consensus, as opposed to every node on the network. Thus, the UNL represents a subset of the network which, when taken collectively, is trusted by S to not collude in an attempt to defraud the network. Note that this definition of trust does not require that each individual member of the UNL be trusted. Proposer. Any server can broadcast transactions to be included in the consensus process, and every server attempts to include every valid transaction when a new consensus round starts. During the consensus process, however, only proposals from servers on the UNL of a server S are considered by S. Formalization. We use the term non-faulty to refer to nodes in the network that behave honestly and without error. Conversely, a faulty node is one which experiences errors which may be honest due to data corruption, implementation errors, etc., or malicious Byzantine errors. We reduce the notion of validating a transaction to a simple binary decision problem. Each node must decide from the information it has been given on the value 0 or 1. As in Atiyah, Dolev, Jill, 1984, we define consensus according to the following three axioms. C1. Every non-faulty node makes a decision in finite time. C2. All non-faulty nodes reach the same decision value. C3. 0 and 1 are both possible values for all non-faulty nodes. This removes the trivial solution in which all nodes decide 0 or 1 regardless of the information they have been presented. Okay, so I'm just going to go ahead and say it. So far, reading this, it hasn't told me why this is a good investment. This just tells me like what this consensus is, like how the consensus works. All right, cool, but this doesn't tell us why we should be investing in Ripple. But, let's continue reading. Existing consensus algorithms. There has been much research done on algorithms that achieve consensus in the face of Byzantine errors. This previous work has included extensions to cases where all participants in the network are not known ahead of time, where the messages are sent asynchronously. There is no bound on the amount of time an individual node will take to reach a decision, and where there is a delineation between the notion of strong and weak consensus. One pertinent result of previous work on consensus algorithms is that of Fisher, Lynch, and Patterson, 1985, which proves that in the asynchronous case, non-termination is always a possibility for a consensus algorithm, even with just one faulty process. This introduces the necessity for time-based heuristics to ensure convergence or at least repeated iterations of non-convergence. We shall describe these heuristics for the Ripple protocol in section 3. The strength of a consensus algorithm is usually measured in terms of the fraction of faulty processes it can tolerate. It is provable that no solution to the Byzantine generals problem, which already assumes synchronicity and known participants, can tolerate more than n-1 divided by 3 Byzantine faults, or 33% of the network acting maliciously. This solution does not, however, require verifiable authenticity of the messages delivered between nodes, digital signatures. If a guarantee on the unforgeability of messages is possible, algorithms exist with much higher fault tolerance in the synchronous case. Several algorithms with greater complexity have been proposed for Byzantine consensus in the asynchronous case. FAB Paxos 5 will tolerate n-1 divided by 5 Byzantine failures in a network of n nodes amounting to a tolerance of up to 20% of nodes in the network colluding maliciously. Atia, Doyev, and Jill introduced a phase algorithm for the asynchronous case, which can tolerate n-1 divided by 4 failures, or up to 25% of the network. Lastly, Al-Khiri et al. 2008 present BFT Cup, which achieves Byzantine consensus in the asynchronous case even with unknown participants, with the maximal bound of a tolerance of n-1 divided by 3 failures, but with additional restrictions on the connectivity of the underlying network. Formal consensus goals. Our goal in this work is to show that the consensus algorithm utilized by the Ripple protocol will achieve consensus at each ledger close, even if consensus is the trivial consensus of all transactions being rejected, and that the trivial consensus will only be reached with a known probability, even in the face of Byzantine failures. Okay, so now we're halfway through this article, and so far it doesn't really tell us why Ripple is such a good idea, but I digress, and these are some of the references. Alright, so let's just keep going. Let's just get through it. Since each node in the network only votes on proposals from a trusted set of nodes, the other nodes in this UNL, DUNL is what the unique node list, okay? And since each node may have different unique node lists, we also show that only one consensus will be reached amongst all nodes, regardless of the unique node list membership. This goal is also referred to as preventing a fork in the network, a situation in which two disjoint sets of nodes each reach consensus independently, and two different last closed ledgers are observed by nodes on each node set. Lastly, we will show that the Ripple protocol can achieve these goals in the face of n-1 divided by 5 failures, which is not the strongest result in the literature, but we will also show that the Ripple protocol possesses several other desirable features that greatly enhance its utility. Okay, here we go. We're going to be talking about utility of Ripple. Ripple consensus algorithm. The Ripple protocol consensus algorithm is applied every few seconds by all nodes. In order to maintain the correctness and agreement of the network, once consensus is reached, the current ledger is considered closed and becomes the last closed ledger. Assuming that the consensus algorithm is successful and that there is no fork in the network, the last closed ledger maintained by all nodes in the network will be identical. 3.1 definition. The Ripple protocol consensus algorithm proceeds in rounds. In each round, initially, each server takes all valid transactions it has seen prior to the beginning of the consensus round that have not already been applied. These may include new transactions initiated by end users of the server, transactions held over from a previous consensus process, and makes them public in the form of a list known as the candidate set. Each server then amalgamates the candidate sets of all servers on its UNL, unique node list, and votes for the veracity of all transactions. Transactions that receive more than the minimum percentage of yes votes are passed on to the next round if there is one, while transactions that do not receive enough votes will either be discarded or included in the candidate set for the beginning of the consensus process on the next ledger. The final round of a consensus requires a minimum percentage of 80% of a server's UNL agreeing on a transaction. All transactions that meet this requirement are applied to the ledger, and that ledger is closed, becoming the new last closed ledger. Correctness. In order to achieve correctness, given a maximal amount of Byzantine failures, it must be shown that it is impossible for a fraudulent transaction to be confirmed during consensus unless the number of faulty nodes exceeds the tolerance. The proof of the correctness of the Ripple protocol consensus algorithm then follows directly. Since a transaction is only approved if 80% of the unique node list of a server agrees with it, as long as 80% of the unique node list is honest, no fraudulent transactions will be approved. Thus, for a unique node list of n nodes in the network, the consensus protocol will maintain correctness so long as f greater than or equal to n-1 divided by 5, where f is the number of Byzantine failures. In fact, even in the face of n-1 divided by 5 plus 1 Byzantine failures, okay, so I guess the 5 is because each one leading up to 5 is 20%, something like that. Correctness is still technically maintained. The consensus protocol process will fail, but it will still not be possible to confirm a fraudulent transaction. Indeed, it would take 4n plus 1 divided by 5 Byzantine failures for an incorrect transaction to be confirmed. We call this second bound the bound for weak correctness and the former the bound for strong correctness. It should also be noted that not all fraudulent transactions pose a threat, even if confirmed during consensus. Should a user attempt to double spend funds in two transactions, for example, Even if both transactions are confirmed during the consensus process, after the first transaction is applied, the second will fail as the funds are no longer available. This robustness is due to the fact that transactions are applied deterministically and that consensus ensures that all nodes in the network are applying to the deterministic rules for the same set of transactions. For a slightly different analysis, let us assume that the probability that any node will decide to collude and join a nefarious cartel is PC. Then the probability of correctness is given by P asterisk, where this probability since likelihood that the size of the nefarious cartel will remain below the maximal threshold Byzantine. Okay, so can we copy this actually? Okay, let's see if we could put this in like